Hello friends, welcome to this session. In this session, we are going to take some of the numerical torsion terms. In the earlier video lectures, we gone through the torsional equation, torsion formula and their related numerical problems we solve. So in this video lectures, we will take some of the terms related to the torsion. The first term is the torsional flexibility. The, this torsional flexibility is a angle or twist which is required for the unit torque. So for the unit torque, how much twisting angle makes with the original line or original length of the shaft. So that angle of twist for the unit torque, it is called as the torsional flexibility. So as per the torsional equation, we know the formula T upon J is equal to G theta divided by L. So as per this definition of torsional flexibility, the unit torque means that T value is equal to 1. So how much for the T is equal to how much twist or angle of twist it makes at the center of the shaft. So that can be determined or that can be solved by using this, or we'll get that theta value as per this torsional equation. So that ultimately that theta is equal to L divided by Gj. Putting that torque is equal to 1. So we'll get this particular formula, and that theta or that twist is in radian per Newton meter. Second important term is the torsional stiffness. Torsional stiffness is the torque required for unit twist. So this torsional stiffness is exactly opposite to the torsional flexibility. So in the flexibility there is a twist required for unit torque, and here in the torsional stiffness the torque required for the unit twist. So unit twist means that theta value you have to take here is equal to 1, and again same equation the use here, and only just putting that value of theta is equal to 1. So we'll get that required torque for the unit twist, and T, that torque is equal to Gj divided by L. So G is the modulus of rigidity or section modulus, J is the polar moment of inertia about ZZ axis, and capital L is the length of the shaft. And that torque value or that torsional stiffness is in Newton meter per radian. Next important term is torsional section modulus. So for that there is a one figure I have drawn which has all the three axes. So there is this is a cross section of the shaft. There is a x axis exactly perpendicular. There is a y axis, and along the length or along the shaft or along the longitudinal direction, that direction or that axis is the ZZ axis. So we'll see that torsional section modulus here, ratio of polar moment of inertia to radius. So polar moment of inertia is J, to radius it is called as that torsional section modulus. So that value it is in meter cube. After that we know that moment of inertia in the engineering mechanics. We studied that moment of inertia about different axes. So for x axis and y axis, as per this cross section of the shaft, that moment of inertia is pi by 64 into d raised to 4. So this is the moment of inertia I, and x and y direction, that moment of inertia is same. So as IZZ axis, ZZ axis is the longitudinal axis or the along the length of the shaft, that axis is the ZZ axis. So IZZ is moment of inertia is equal to J. So that IZ moment of inertia about ZZ axis is nothing but the polar moment of inertia, and that polar IZZ axis can be determined by taking the summation of xx and yy moment of inertia. So putting that ixx plus iyy, so we'll get that relation pi by 32 into d raised to 4. So this is our relation we required for the polar moment of inertia about ZZ axis. It is a pi by 32 into d raised to 4. So this is what that our polar moment of inertia is coming, or it is coming from the moment of inertia about both of these axes. So for solid shaft, the polar moment of inertia is taken this value J is equal to pi by 32 into d raised to 4, and for a hollow shaft which has a two diameter, external diameter and internal diameter, at the time the formula becomes pi by 32 d raised capital D raised to 4 minus small d raised to 4. Polar section modulus is J divided by R, that J is the polar moment of inertia, R is the radius of the shaft. So put R radius is equal to d by 2, d is the diameter, and putting that polar moment of inertia in this formula, so we'll get that polar section modulus, which is ultimately at pi by 16 d cube. So after solving this polar J by R polar section modulus, we'll get that polar section modulus in this value pi by 16 d cube. So this is a torsion section modulus or polar section modulus. After that, torsional rigidity. Torsional rigidity is the product of shear modulus and moment of polar moment of inertia. So this definition, you remember this, that is it is a multiplication or product of shear modulus G and polar moment of inertia J, and that unit of that torsional rigidity is Newton into meter square. So that torsional rigidity value can be determined by taking the formula Gj G into J, and the unit is Newton into meter square. Maximum shear stress. So many of the times we in the problem they ask to determine the maximum shear stresses. So maximum shear stresses can be determined by again we have to look at to the that torsional equation, that is the tau upon R is equal to T upon J. So tau is equal to T into R divided by J. So T is a torque, R is the radius, and J is the polar moment of inertia. So here it is a polar moment of inertia is written, and T is there, and d by 2 is the radius. So after simplifying, we will get this 16T divided by pi d cube. So you can directly determine the maximum shear stress tau by using this particular formula. This is the relation. After that, power transmitted by the shaft. So many of the times the torque is applied to the shaft, and that torque is transmitted the power. That's why for the how much power is transmitted by the shaft with the torque, so that can be determined by in this particular formula. So here in this that Kn is the number of revolution per minute, Ta is the average torque, F is the force in kilonewton, and radius in meter. So first of all, work done. We knows that work done can be determined by force into distance move per minute. So force is symbolically capital F, and distance means though the shaft is circular section, that's why that per minute there is a distance onto the circumference of the shaft can be determined by 2 pi r, and n is the number of revolution, right? So if it is number of revolution is known, so you can determine the total distance moved by per minute. So that force into distance will get that work done per minute. So as the torque is known is the force into radial distance. So this relation if you put here, so you can F into R, you can directly put that torque, so you will get 2 pi nt. So this particular relation, this is the work done per minute. If you want to determine the work done per second, at that time only you have to divide this relation by 60. So ultimately our relation becomes work done per second 2 pi nt divided by 60. This value is in kilonewton into meter, and that is nothing but the power transmitted by the shaft. So this power transmitted by the shaft is nothing but the work done per second. So this is work done per second is nothing but the power transmitted by the shaft, and that value is kilonewton into meter, or it is represented in kilowatts. So kilonewton into meter means kilowatts. So ultimately this power transmitted by the shaft P is equal to 2 pi nt divided by 60 kilowatt. So here it is a relation, it is written here. So kilonewton into meter means kilowatt, or Newton into meter means W here it is a watt, kW is the kilowatt. Finally, the strength of solid shaft, or it is also called as a safe torque. So we know that turning force is the shear stress into area, means ultimately shear stress formula force divided by cross section area, or turning force is equal to shear stress into area. So strength of the solid shaft, or we can say it is a safe torque, can be determined by, again we have to look at to the torsion equation, and this torque can be determined by tau j divided by r. So this is the strength criteria as per the strength criteria equation. So tau j is the pi by 32 into d raised to 4, r is the radius, can be determined by d by 2, So putting all these values, we will get that torque, which is a tau max as per the strength criteria equation. This is the overall torsion formula, torsion equation, and tau max will get the tau pi dq divided by 16. So this relation means for the strength of the solid shaft can be, or it is also called as a safe torque or maximum torque, can be determined by using this formula. So you remember this formula because the further problem are also based on this particular formula. And strength of this is for a solid shaft, and there is a one more hollow shaft. The strength of the hollow shaft or strength of the hollow shaft or safe torque of the hollow shaft can be determined by this formula. So only just putting these values that and ultimately we'll get the relation pi by 16 into d raised to 4 minus d raised to 4. Capital D is the external diameter, small d is the internal diameter, and divided by d into tau. So by using this relation, you can determine the safe torque for hollow shaft, and this relation for safe torque for solid shaft, which has a single diameter, hollow shaft which has a two diameter, external diameter and internal diameter. So in this figure you can see that there is a cross section of the shaft, circular shaft. Internal diameter is small d and external diameter is capital D. So by using this, only you have to remember this formula, or it is also called as the safe torque. So strength of the solid shaft, it is also called as the safe torque, and strength of hollow shaft, and this is a value of safe torque for hollow shaft. That's it here. Thank you very much.